Good morning. So welcome to our today's physics class. So hope you understood previous classes, yesterday's classes. Today we are starting with a new chapter. So today we will start electromagnetic induction. So our class will be about electromagnetic induction. After electromagnetic induction, we can go to AC and we will deal some important problems from this one. And in between the class itself, we will discuss how to solve problems or what are the types of questions which can come from this area. So in this electromagnetic induction, we'll start with the experiments of Faraday and Henry. So you know the experiment done by Faraday and Henry, the same experiment you done in 10th standard also. One second. Okay, so we already done this experiment in 10th standard. Now what we are going to do is we will do this one in detail. We have to see what is happening in this one. So in this experimental setup, we have a coil here, and that coil is connected to a galvanometer. And we have a magnet here. So you know what is a galvanometer because in the last class you studied about the galvanometer. So the purpose of the galvanometer here is the galvanometer shows the direction of current. So when you have a galvanometer here, if there is a current in this one, it will show the direction. So if you take an ammeter, we can measure the current. But in the case of an ammeter, you know what happens in the ammeter, we have a 0 and we have the continuous readings in that one. But here, this is not for taking or the measuring the how much is the current. We just want to see whether there is a current and what is the deflection, whether it is toward that side or this side, that is in which direction we have the current. That's what we have to see. So for that one, we have a coil here and we have the magnet here. And just like the galvanometer, you should know something about the magnet also. So in junior class you studied, we have a magnet, and for the magnet we have a north pole and south pole. So actually if you have a magnet like this, we have north pole here, south pole here. What is the difference between this north pole and south pole? Generally, people feel that this is two different things. That is one positive charge, just like negative charge. We have north pole and south pole separate. Actually, if you think in a higher level, this north pole and south pole is actually the same thing. For example, if you cut this one like this south pole becomes, this side of the south pole becomes north pole. So if you take a magnet, the reality is that for a magnet, we don't have separate this north and south. When you look from this side, it becomes north. The same north, if you cut here, and if you look from this side, that is south. So this north and south depends on from where you are seeing. That is, from this side, it is north. So when we study the direction of current and all, you will get clear idea about that. So in this magnet, we have the north pole this side. So this side we have the magnetic field lines coming like this. And the importance of this one is very close to the north pole, this area here. Here we have a very high magnetic field. That is, the number of field lines are very high, or the number of field lines are very close here. When the field lines are very close, it means the magnetic field is high there. And when we come toward this side, here the magnetic field lines are away. So the magnetic field is less. So when we move this magnet toward this side, what we are actually doing, in 10th standard, we are just discussing that we are moving the magnet. So here, when you are moving the magnet, actually what we are doing is, this magnet's field in this coil is here, it is very less. When you move it toward this side, the magnetic field increases. So that's the main point. We are making this coil to subject to a magnetic field which is increasing. So when you push it toward this side, the magnetic field increases. So when there is an increase in the magnetic field in the coil, then what will happen? It will show a deflection. So that's very important. That is, when there is a magnetic field and that magnetic field increases, it shows a deflection. And you already studied in 10th standard, if it is not increasing, if it is constant, it will not show any deflection here. That's also important. When you keep a coil in a magnetic field, it will not show any deflection. This is very basic thing, but why I am stressing on this one means this is important when we are coming to the next part of the topic. So when we are increasing the magnetic field where the coil is there, then what will happen? Our galvanometer will show a deflection. Now, if you keep it permanent inside this one also, we have a very high magnetic field, it will not show any deflection. Now the next part is, if you take it away, then what happens? When you keep inside, the magnetic field is very high here. When you take it away, the magnetic field reduces. When the magnetic field reduces also, this galvanometer will show a deflection. But there is a difference. When it moving toward this side, that is from lower magnetic field to higher magnetic field. The coil is in lower magnetic field, then it becomes higher magnetic field. It will show one deflection. And when you are taking it away, it is from higher magnetic field to lower magnetic field. That time the deflection will be opposite. That point is very important. So here the most important point is, if you simply keep in magnetic field, it will not show any deflection. When the magnetic field increases, it shows a deflection. When the magnetic field reduces, it shows a deflection, but that is in the opposite direction. Now the same thing we can do with the other side of the magnet. If you inverse this one, that is, instead of north here, if south comes here, the same phenomena will happen. But when we are taking towards this side, taking south toward this side is same as taking north away from this one. So if you go in general, the thing is, when you are changing a magnetic field, it shows a deflection. If the direction of the magnetic field is changed, then again the direction of this deflection also will change. So this is the simplest example of this electromagnetic induction. So here we will go for a higher level, or the next step for this one, where we will replace this magnet with a coil. So you already studied in the previous chapter a current carrying coil that acts like a bar magnet. So we can replace this magnet with a current carrying coil. So here that is done. So here you see we have two coils. We have one coil here, so that is attached to a galvanometer. And we have another coil here. So this coil is kept a little bit away. And here we have connected a battery. So very important, what we connected here, this one is a DC source. It is not AC. It's a DC source. Normal battery is connected. So when normal battery is connected, the importance is when current is passing through that one, it will produce a magnetic field. That magnetic field also will be constant. So that is a constant magnetic field. It is just like a bar magnet only. But that is different in the case of AC. That's why I am stressing on that one. It is not AC. We have a DC source here. When a DC source is kept here, a current is passing through this one and it produces a magnetic field. And now this coil is kept in its vicinity. So there is a magnetic field here, and you can see there when it is kept here in rest, it will not show any deflection because it is same as keeping a bar magnet. So when a bar magnet is kept near to a coil, there will not be any deflection. So here also there is no deflection. But now if you move it toward this side, when you move it toward this side, this galvanometer will show a deflection, same as the bar magnet. And when we take away, the deflection will be in the opposite direction. So it is also same as the bar magnet. That is, when you're taking north toward this side, it was showing a deflection. And when you are taking away, it will show a deflection in the opposite direction. But here one question comes, there we have changed the north and south. So here, how to change the north and south? This battery you can invert. If the battery direction or the current direction changes, then when you change it, it is same as changing the north and south. So when you move toward this side, it will show a deflection. When you move towards the opposite side, it will show another deflection in the opposite side. So that's about the second part. So the first part and second part, both are actually same only. In both cases, the important point is, here it is showing a deflection when there is a change in the magnetic field. That is very important. Magnetic field alone is not making any deflection here. It makes a deflection only when there is a change. Now, this is in the case of a DC connected here. Now, we are going to a next level where we are using similar setup, but we have a key here. So in this case, we are not moving this one. We have one coil here. This is same of the previous setup. This one also same. In the previous setup, what we done? We moved this coil toward this side, or we moved the coil toward that side. So now what we are doing is, we are not moving it. We are going for another method. Instead of moving the coil, what we can do? We have a key here. So here, when the key is open, no current is passing through this one. So the magnetic field is 0. When no current is passing through this one, the magnetic field is 0. Now, we have to increase the magnetic field. To increase the magnetic field, what we are doing is, we are just switching on this one. So you should know one thing, when you are switching on this one, the magnetic field changes from 0 to a high value. So it goes to the maximum. It takes some time. That's very important. Magnetic field, when a magnetic field is set up in a coil, it is not an instantaneous thing. It takes some time from 0 to maximum. So it's when you switch on this one, it increases to a maximum value. So there is a change in the magnetic field. That time, this will show a deflection. This needle will show a deflection towards any one side. But once it is switched on and kept like that, the magnetic field is constant. That time it will come back. That is very, very important. I am stressing on all these things because now you have competency-based questions. So much questions can come based on this one. Such an experiment is given and so much question can come. So previously this topic was considered as not that important because already studied in 10th standard. But now it is not like that. The situation changed. You have questions, competency-based questions. So a simple experiments can be given and detailed questions can come from that one. So you have to give stress on such simple concepts also. So when this is switched on, this shows a deflection. And when you keep it switched on itself, there is a magnetic field. It's a very strong magnetic field. Still, it will not show any deflection. The reason for that one is, there is no change in the magnetic field. We need a change in the changing magnetic field is required. Now, the thing is, when you open this one, if you open the key, then the magnetic field, what happens from the maximum, it is coming towards 0. So when it is coming from a maximum value to 0, then also it will show a deflection. But that time the deflection will be opposite. So why these things happens, that we will discuss later. Now we are discussing about the experiments done and the result of the experiment. So they observed that when the key is switched on, it shows the deflection towards one side. And when you keep it switched on, there is no deflection or there is no induced current in this one. But when you switch off that one, or when the key is opened, at the time of opening, it will show a deflection toward that side. Again, it will come back to 0. So that's our experiment. So now, what is the total result of all these things? So we have seen here 3 things. This is the first one, and second, we have the second one here, and we have the third one here. So what is the total result of all these things? So if you carefully see all these things, the total result is when there is a magnetic field, it is not producing any current. When there is a changing magnetic field can induce a current in the nearby coil. That is the most important thing. So our main point is the changing magnetic field induces a current in the nearby coil. This one also you study in 10th standard. But in 10th standard, how much is the induced current, that we not study. So in 12th standard, we have to study about how much is the induced current and how it depends on the change, that also. So that details are given in Faraday's laws. So from here, we have to go to Faraday's laws. So in Faraday's law, we will study how much is the induced EMF. And if you know the induced EMF and what is the resistance connected doesn't mean that we have to connect a separate resistance outside. If this coil itself may have a resistance, so if it is a closed circuit, that itself will make a current. So how much is the current passing through that one? So all those things we will study. So we'll move to the next part. So we'll before studying this Faraday's law, we should know about the magnetic flux. So in electrostatics, we already studied electric flux. There we studied the electric flux, which is written by phi like this. Here we have the magnetic flux, and the magnetic flux is given by the same phi only. To identify it as magnetic, we will write B, phi B we will write. This B is for magnetic. So what is this magnetic flux actually? So you might have studied the definition of this magnetic flux, but here we have to know, you should know what is physically this one, because then only you can answer the questions based on that one, especially the competency based questions. If you want to answer, you should know what is the thing or how it works. So the magnetic flux, generally people have a confusion in that one. People think that the number of field lines passing per unit area like that. It's not like that actually, because it is not about unit area, it is about the total area. So you have the field lines like this, and we have an area here. So the first thing you should know is these field lines, how many field lines are there? That depends on the person who is drawing that one. When you are drawing this magnetic field line, one person can draw like this, one person can draw more close lines. So actually, these magnetic field lines, the density of the magnetic field lines shows something. That is, it's a comparative thing. In the case of our bar magnet, you can see you have a bar magnet here. The magnetic field lines are going like this. So what is this one? This area which is close to this magnet, this area we have more field lines. This area here we have less number of field lines. So that says that here the magnetic field is strong and here the magnetic field is weak. But another person can draw more number. So it's a comparative thing. So we have different number of magnetic field lines there. So that's why when the definition of this magnetic flux comes in, magnetic flux through a plane, if you take in most of the area, we will tell it is a number of field line like that. But you should know this number of field lines is a comparative thing. Okay, it is not exactly counting how many lines are there. It just says that comparing to this area, here magnetic field is more or less like that. But this magnetic field lines, it depends on the number only. Actually, the number says whether it is strong or less, but it is not exactly counting the number. Okay, so that's about the magnetic field. Now, what is this magnetic flux? When you have the magnetic field like this, see here, if you have an area kept here, you have an area here like this. So some number of field lines are passing through this one, or how much field is passing through that one. That total number of field lines or total amount of field passing through that area, that is called as magnetic flux. So it is not the per unit area. You have a big area means more field lines will be there. So the flux will be more. I think that concept is clear. That is, you have an area like this, and so many number of field lines are passing through this one. If this area is big, more field will pass through that one. Instead of this field, if you think about light or water, it will be more easy for you to understand that. When you think about some water is flowing in a stream, and you have a square shaped frame. You are keeping that frame in the water, means how much water is passing through that frame. That is the flux actually. So you can see the amount of water passing through that particular frame which you keep in the water. That depends on what actually? That depends on the flow of water through that stream. So that flow is actually our magnetic field. If more water is flowing per second, like that we have the magnetic field passing through that one. And one more thing, if the area is large, then what will happen? When the area is large, more flux will be there, more water will pass through that one. Same concept you can think. There is one more point in that. And you think about that frame which you are keeping in the water and how much amount is passing through that one. So the flow of water, we taken it as the magnetic field, and the area also we taken. Now you think about, you are turning that area, instead of keeping it straight like this, you are turning a little bit. Then the amount of water passing through that one will be different. Same way, the magnetic flux also depends on the area here and also on the angle. To make it some more clear, you see here, your magnetic field is like this. If your area is straight like this, means entire field lines will pass through that. Now, if your area is kept like this, if your area is like this, I am taking the area like this. When the area is kept like this, what happens actually? The number of field lines reduces a little bit. When you keep it straight like this, it's more. Actually, in this one, is if you notice carefully, you can see how many field lines are passing this area. That only crosses through this area, not the total area. This side only we have to take. So if you take this side, how you can get this side? This is a particular area, and here in this case, we are taking area as a vector. When you take area as a vector, it is having a direction. So if your area is like this, A, when you take area as a vector, the direction of area is like this. That is very, very important. Generally, area is actually length into length. It's a scalar quantity. But in here in such cases, when you take the flux, you will take area as a vector. When you take area as a vector, vector should have a direction. So direction of area vector will be perpendicular to the actual area. That is, if you take my palm here, its area, you can take this length into this breadth or something like that, and the direction is like this. So the direction is like this. Okay. Now, so for this area, we have the direction in this way. So this makes an angle theta here. So if you check here, the same theta will come here also. So this area will be, this is A, this area will be A cos theta. So the important point is how much flux is passing through that one. That depends on this side area, not this side area. So this A cos theta is important. That's why our flux is coming like this. Flux phi B is equal to the magnetic field B into A cos theta will come. I think why this A cos theta comes, that concept is clear, because we are taking not this area, how much area which is facing this magnetic field lines. That, so this area is A, means this side area will be A cos theta. So we have B A cos theta, or we will write it as B dot A. So the flux, magnetic flux is B dot A. So this we can tell it as it's a measure of number of field lines passing perpendicular to the area. But the point is we have B A cos theta. This angle also is very important. Now you see here, when the field line is this way, if your field is this way and your area is this way, area is like this, means area will be like this, the area vector will be like this. So no field line is cutting completely, the field lines are going above and below, so that it will be like this. So we have a zero flux through that one. If you keep like this, you have the maximum flux. That's how we have to deal it. So our magnetic flux is given by B dot A or B A cos theta. How this B A cos theta is coming, or what is the importance of that one, that's what we discussed here. Here also in this diagram also it is explained, the same thing is explained here, how this flux becomes B A cos theta or B dot A. And you can see that this is a scalar product. So this flux will be a scalar quantity. This magnetic flux, just like electric flux, it will be a scalar quantity. We are taking a dot product here. So that's about magnetic flux. So the main point what you have to remember is magnetic flux means it is depending on the area and also depending on the angle. So if more area is there, more flux will be there. It is not magnetic field per area or something. It is actually field into area. Flux per area becomes magnetic field, just opposite. Okay. Now we will move to the next part. So we have the Faraday's laws of induction here. So in Faraday's laws, we are using the flux word here. That's why we study the flux now. So here you can see the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. That is how much EMF is induced in that one. That depends, that is actually equal to the time rate, that is rate of change of flux. The rate of change of magnetic flux is EMF. So here in this Faraday's law, we are getting the clear idea about how much is the induced EMF. In the previous experiment, we just discussed there will be a induced EMF. Here it clearly says the induced EMF E will be is equal to rate of change of flux, d phi b by dt. So we have EMF is equal to d phi b by dt. Now, this is the case if you have a particular loop, that is you have a magnetic field like this. In this magnetic field, you have a loop, a circular loop or a rectangular loop. We have this equation. But you know, in most of the cases, this is not a single loop. We will have many number of turns in this one. It will be like a coil with many number of turns. N number of turns will be there. So when this N number of turns are there, so that it is given by d phi by dt, same thing. And you have to multiply with the number of turns. This N is the total number of turns you have to multiply. So this is for a single loop. And when we have many number of turns or many number of loops, we have to use this one. Okay, now, but what I written here and what is already here, there is a difference. There is a negative sign here. So why this negative sign comes here, that we will discuss after this one. That is the next topic actually. Now, what is the main point in this one? If this is constant, that is if the magnetic flux is constant, then EMF will not be there. That's what we discussed in the experiment also. There should be a change. Now, this one, if the magnetic flux is given as an equation, you have to take the derivative of that. Sometimes the magnetic flux may not be given as an equation. It will be given as the initial magnetic flux is this one and final magnetic flux is this one. This change happens in 2 milliseconds or 2 microseconds like that. So directly you, instead of taking d phi by dt, you take it like a delta phi by delta t, because in numerical problems it will come like that actually. Instead of giving an equation for flux, they will give the magnetic flux changes from 10 to 5 or 5 to 10 in a time of 2 milliseconds or 2 microseconds. So directly you can take what is a change here, the final value minus initial value divided by the time. So that's how you can do. That I am stressing on that one, because when problem comes like that, initial value and final value, people will have a confusion. You taken as d phi by dt. So can we use it as delta phi by delta t? You can do it like that also. Most of the 1 mark question and also will come like that only. So directly we can use. So that's about Faraday's law. So Faraday's law says that the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. And the equation is this one. This is the general equation. And when we have n number of turns, we can use this one. And we have a negative sign here. So now we will discuss why a negative sign came here. So we will go to the negative sign part of this one. So that is very, very important. These things actually, whatever we discuss now, it's not something new to you. Whatever you know, that's only we discussed once for just like a revision we done. Okay, now we will move to this one, this Lenz law. This Lenz law is the reason for this negative sign. Why this negative sign comes here means you have to tell this negative sign is due to Lenz law. Okay, this Lenz law. So what is this Lenz law? So we will go for that one. Okay, so that is our induced EMF E is equal to d phi b by dt. This much we are getting from Faraday's law. And we have a negative sign here. And this negative sign is due to Lenz law. So now we'll go for this Lenz law, how this negative sign comes here. So this Lenz's law states that first we will go for the statement, then we will explain that one, because this one also very important in the case of our case studies type questions and 1 mark question where you have to apply. So in application level, you will get a question surely from this one about the Lenz's law. Actually, directly asking the question for writing the Lenz's law is it's a less chance now in our modern type of question papers. We will have a situation where you have to apply Lenz's law. So you should know what is Lenz's law, how we can apply. So after this one, we have 1 or 2 examples how we can apply Lenz's law. So you should be careful about the Lenz's law first. After that, how to apply. So you see here what the Lenz's law says. The polarity of the induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it. That is, in the previous case, here we have a magnetic flux, and in this case also we have a magnetic flux here. So this magnetic flux induces a current in this one. So this current will have a polarity. That is, polarity means the positive, negative, or the direction, which side will become positive and which side will become negative. That's called as polarity. The induced current will have a polarity. That polarity will be in such a way that it will oppose this one. Once more, the polarity of the induced current will be in such a way that it will oppose the magnetic flux that produced it. So that's why we have a negative sign here. That is, it is opposed to the flux produced it. So this which opposes this point, we will take in detail how it opposes. So here we have 2 pictures, which is a very simple explanation of this one. So Lenz's law, how it works. Okay. So here you see, we have a north pole which is going towards, this is a north pole, and you have a loop like this. In your examination also, you should be very much careful. This loop, when we are drawing, we have a confusion. This loop, this line you see here, it is up to the center. So you should know whether it's clockwise or anti-clockwise. That logical view you should be there. When this line is given up to the center, its meaning is this line is this side and this line is inside. This is like this. Okay, if this is up to here and starts from here, means this line is behind and this line is front, because this is a 3D thing, 3-dimensional thing, and your question paper, this will be in 2 dimensions. So you should watch this one carefully. This one is going up to the center. So the meaning is this is back side and this is front side. So your loop is like this. So here also same thing. This is the back side, and because it's like this, this is back side and this is front side. Now, when you push this north pole toward this side, here some induced current will be there. So what our Lenz's law say that it will oppose this one. So opposing north pole, we have a north pole, we are pushing the north pole toward that side. This one opposes. Which can oppose a north pole? If you want to oppose a north pole, here also it should be north pole. So to oppose a north pole, we need a north pole here. So I told you already in the case of that bar magnet, whether a pole is north or south, that depends on from where you are seeing. So when a current is passing in this loop, if you have a loop like this where the current is passing, see here, if the current is passing like this, the magnetic field line is toward this side. So you can see that it is like this. So same thing, if the loop is like this side is north and this side is south. So there is no separate north and south. A particular current loop can be north or south according to the position of the observer. When you are looking this loop from this side, this is north. The same loop, if I go and look from this side, then it is south pole for this one. Now you see here, when you push this one, this loop, in this loop, there will be a current, induced current that we discussed already. The current will be d phi b by dt. So there will be a current in this one. So our problem is to find the direction of current, whether it will be that side or this side. So what this says, this should oppose. So this is north, means this side also should be north, then only it can oppose. So those who not understood, once more I will tell you the concept. See here, you have a magnet with the north side here. You have a loop here. When you push this north side toward that side, as per Lenz's law, it should oppose. So to oppose, this side should be north. So north and north will oppose. I think that's clear now. Now, if you want a north in this loop, what should be the direction of current? You have to use the right hand screw rule. So if you want north here, north means the current, the magnetic field direction will be this side. So it should be like this. That's what it says. So the current should be like this. If the current is like this, then only you can, like this means from when you are looking from this side should be like this. Okay, so you will get a north here like this. So to remember that one, a method also they told you can write n like this. So this will be north here. So this loop will have a current like this, which will be north when you see from this side. And if you see from this side of this loop, this will be south, because the loop is like this. So the magnetic field is from this side to that side. So here it will be north, and this side it will be south. So from this side we are getting a north. So this one opposes. Now the next part is, if you pull this one back, what will be the direction of current in this one? When you pull this one, when you pull the north back, again it should oppose. You are pulling it back. So how to oppose it? You are pulling this side, opposing that one means you have to push that one toward that side. So if you want to push this north toward that side, it should be south. That is, see here, you have the loop here, and your north is going away from this one. North is going toward this side. So it is going away. You have to attract this one. So this side should be south. So if you want to get south here, the direction of current should be like this. So I think that's clear. That is, when you push north here, north should come so that it will repel. When you take the north away, what should happen? Here south should come. Then only it will pull. So it should always oppose. And in this picture, you see, we are taking the north this side, and the south is coming like this. So this is this same thing what we discussed here is in this picture. Now it can come in the opposite way also. That is, instead of north, if south comes here, what will happen? When you push south here, it should repel. So it should be so, pulling a north this side and pushing a south toward that side, both are same. When you pull a north this side, here south will come. If you push south toward that side, it will come. Actually, if I tell it many times also, for you to make it clear, you have to draw this one. You have to take this magnet and you try yourself 2-3 times. You draw this north comes means whether you are able to draw it, and south. And once more, if it is already you are getting a solve from the book, you have to compare it, because it's not just by seeing this one. Because you should be able to do it, because the next part is more confusing. That's why this concept should be clear. So the main point is the induced EMF should oppose, and this negative sign shows that it is in the opposite direction. So once more, we have Faraday's law here. In Faraday's law, it says that E is equal to d phi by dt, and we have a negative sign here, and this negative sign is due to Lenz's law. So Lenz's law says that the induced EMF tends to produce a current which will oppose the magnetic flux that produced it, and how it is opposing, that's also discussed here. Now we will go for applying that one. So this is a textbook question, and this is a question which is generally asked. I have not written the question, just the situation only I written here. Now here you can see this magnetic, there is some magnetic field here. This magnetic field is, here you can see cross is there. I don't know whether it is visible, it's a very small cross. So I will make it a little bit bigger, no problem. So we have the cross like this. When it is cross like this, what is the meaning? The magnetic field is into the plane of the paper. Okay, in examination, you have to use the proper terms. When something is like this, it is, you don't write it as downwards, upwards, and all, because you are writing on the paper. So your answer should be, when it is toward that side, you have to write into the plane of the paper. Sorry, if it is if it is coming toward this side, you have to tell it's away from the plane of the paper. Okay, so that direction is very important in the case of magnetic field. If north, south and all is given in the question, you write it as north, south and all. When north, south is there also, this side is north and south, and east and west you write. So this is east and this is west. And if it comes like this, then it is upward. And if it is going, because when you have north and south, you have to think on the floor, on the ground. So this side will be upward and this side will be downward. And in such cases, it is not about north, south and also what you have to do is, here we have to mention this one as into the plane of the paper. And if it is toward this side, you have to tell it as away from the plane of the paper. Now our magnetic field is into the plane of the paper. Now the question is, here we have three shapes. We will think about this shape. This triangular shape is here. It can be triangle or any shape. We are taking this one out of this field. When you are taking this one out of this magnetic field, here the magnetic field is high. Listen carefully. The magnetic field is high. Here the magnetic field is low. So what we are doing? We are taking this triangle from higher field to lower field. So when you are taking from higher field to lower field, what we are doing for the flux? We are reducing the flux inside this triangle. Inside the triangle, we have a flux. When you are taking from here to there, what we are doing? We are reducing the flux. So I think that first point is that one. First, you have to check what happens to the flux, whether you are increasing the flux or reducing the flux. So here it is very clear. This triangle we are taking out, so we are reducing the flux. So when you reduce the flux, what our Lenz's law says that whatever change is there, our induced current will oppose that one. So here we are taking it out. So we have to oppose that one. What we have to do? We have to increase the flux. Once more, we have a triangle. Inside that triangle, we have a field. And due to the area of triangle, we have a flux also. We are taking this triangle outside. So what we are doing? We are reducing the flux. So we are reducing the, when it is coming out, the flux will be reduced. So what our Lenz's law says that, so Lenz's law says, when you reduce the flux, the induced EMF should oppose that one. So it should not reduce. You should oppose. So if it should not reduce, what we have to do? This loop, when it is coming out, inside this one current should be there, which will not allow this one to reduce. So it should support the flux to increase. So this, when it is coming out, inside this one, there should be a current which will produce a flux which is into the plane of the paper itself. I think the concept is clear. Once more, we have a triangle here. In the triangle, we have a field, we have a flux. We are taking the triangle outside. When you are taking the triangle outside, what we are doing? We are reducing a flux which is towards, or sorry, which is into the plane of the paper. When you reduce that one, as per Lenz's law, what it says? It should oppose. So the induced current should be in such a way that the current should produce a magnetic field which is into the plane of the paper. So if you want to get a current which is into the plane of the paper, there again you have to go for the right hand rule. You need a magnetic field. This is the direction of magnetic field into the plane of the paper. So it should be like this. So the current direction should be like this. Like this. Then only it will go there. So we have a current direction which is this way, like this you should get. So how to write this one? So if it is a single word thing, means it should be clockwise. When you look toward this one, it should be clockwise. So this is how we have to deal it. So once more, first you have to check what is the direction of flux. Then you have to check whether the flux increases or decreases. If the flux increases, then what you have to do? You have to try to reduce it. If the flux reduces, you have to try to increase it. So here in this case, the flux reduces. So we are trying to increase it. If you want to increase that one, the current should be in this way. Now the same situation here, this one. This is a rectangular loop here. We are taking the rectangular loop from outside to inside. The situation is same. Here we have low flux here. We are taking it to a higher flux. So from lower flux to higher flux, we are taking. When you are taking from a lower flux to higher flux, what happens? the flux increases. When you increase the flux, what should be our aim? We have to reduce the flux. If you want to reduce the flux, what you have to do? We have to make a current opposite of this one. I think no need of explaining the entire thing again. You should know that it will be in the opposite direction. I think that point is clear. That is how this one is becoming opposite, because here we have from higher to lower, so that it should be in the same direction. Here it is lower to higher. When lower to higher it is coming, what happened? The flux is increasing, so it should be this way. The magnetic field should be this way. So instead of this one, it will be anti-clockwise. It will be this way. Anti-clockwise current will be there in this one. Okay. Now, this is also taken outside. I hope it is taken from outside to inside. This is also taken outside. So there is no difference. This both will be, these two will be same. This is taken inside. Now, one more type is there, which is not mentioned in this one. You see here, it is already kept here. This loop is moving inside this one. When it is moving inside this one, how it will be? You think about that one, because here we have a flux, and here everywhere you have the same flux. It's moving inside the uniform field. Then there will not be any induced flux. So we have three types. One, it is here inside. We are taking it outside. So it will have one type. And when it's from outside to inside, it's one type. And I cannot tell whether it is always clockwise or anti-clockwise, because it depends on the direction of the magnetic field also. If the magnetic field is given as dot like this entire things will become opposite, because this side is the magnetic field. Means the question, you have to check that one first, whether the magnetic field is into the plane of the paper or away from the plane of the paper. That's also important here. And if it is moving inside, how to deal, that also you have to take it. I think that is clear. Now, other than this one more type can come. That also is an interesting type. Here we have a loop like this, in shape. And this loop expands to become a particular shape, because it is a random shape. It expands to become a circle like this. So there will be an induced EMF. That is an interesting thing. That is, you have a random loop that expands to become a circle. So you can see that this circumference is there for that loop, that remains same. So you have a particular length of a loop that will carry the maximum area when it is circle. That you should, that concept should be there. That is, if you have a square or a rectangle or a triangle, anything of this one gets converted into a circle, then what happens? Its area increases. Okay, so it will have maximum area when it is a circle. So when it is in a random shape and changes to circle, what happens? Area increases and the flux will increase, and you have to do accordingly. I think that's also clear. So if any random shape is there that expands to become circle or something like that, you should check whether the area increases. So when area increases, flux increases. So you have to opposite. So it should reduce. So what is the direction you have to take? Now, so we've done so many things on this one. Still, it is not over. We have some more things to discuss about this one. Now, you see here, this is a uniform field itself. You forget about these shapes. I have a shape which is a square. And I have a circle also. Let it be of the same area. Circle is and square is having same area. When I am taking out, the induced EMF will be equal to minus d phi b by dt. When you take it out, this is the induced EMF. In this case, where the induced EMF will be more, whether it will be here or here, you just think about after taking out. Once you forget about this edge afterwards. So that came as a question in many competitive examination and all. So here, what is the difference when you take this one or this one? See here, in this square, first this much part will come out. That time a induced EMF will be there. But in the case of circle, you see here, first this part comes, this much. If it is moving with the same velocity. Here you see here, From this part, the next part when it is coming, the rate of coming out is same. Here you see the next part which is coming out is this much. Next part it is again more. So how much it will come out, that area is different. So what happens is here the rate of change of area is more. So the EMF induced in this one and this one will be different. So you think about that one. If you have a triangle like this, or if you have a rectangle like this, or if you have a circle like this, there will be a difference. Okay, like this you have to think logically, because here you see here always the change will be same. Here the change is different. So the induced, in which case the induced EMF will be more, in which case induced EMF will be less. Such questions also can come. I am discussing so much on this Lenz's law because there is more chance, at least 1 or 2 marks coming also very important for us. 2 marks or 1 marks also very important for our CBSE examination. So you should be very much clear about all types of question which can come in this one. This is another type of question. Okay, this can be like these or like these, both are same only. So you have a current carrying wire like this. A wire carries current like this. Now you have a loop here. This is a loop here like this. And when the current is passing through this one, whether it will induce a EMF here, that's the first question. No. If there is a steady current passing through this one, if the current is steady, then there will not be any induced EMF. The first point is that one. If a DC current or a steady current is passing through this one, it will not induce any EMF in this one. Then when it will induce a EMF, there are so many chances. One is if you move this coil toward this side, or you coil move toward that side, or if you turn the coil, or if you move the wire, in all these cases it will be there. But if both are kept constant there without any change and current is passing through that one, DC, that is if DC current is passing through this one, or a steady current is passing through that one, no induced EMF will be there. Then why the problem comes here? But because in most of the question, it will be a increasing current or a decreasing current, like that question will be there. So you think about this current is, okay, you'll think about this current is reducing. That is, we have a current passing through this wire. This current is reducing. If this current reduces, what will be the direction of induced current in this one? So first, what you should know is, you should find out what is the direction of magnetic field inside this one. First, you forget about whether it is increasing or decreasing. Only think about what is the direction of magnetic field inside this one. So you see here, our current is like this. So the magnetic field will be around. Sorry. So the magnetic field will be around this one. So around this one means 10th standard Fleming's, sorry, not Fleming's, our right hand thumb rule. So if the current is upward, the magnetic field will be like this. The magnetic field goes like this. So in the center, we have a magnetic field which is like this. That is, it is coming toward this side. This side we have like this. I think it is clear. Magnetic field is like this because the current is going up. So first we have to find out that one. In this case, you see the current is like this. So the magnetic field will be like this. Here the magnetic field is coming towards you. Here it is like this. The magnetic field is like this. Now here the question is, this current reduces. So the magnetic field is already toward this side, that reduces. When the magnetic field which is toward this side, that reduces means what is the meaning? As per our Lenz's law, E should be minus d phi by dt. This minus is important for us. Okay. So our magnetic field is this side and that reduces. So what we have to do? We have to increase it, because reducing is the process. We have to oppose it. Always we have to do opposite. So the magnetic field which is toward this side, we have to reduce. So, sorry, it is reducing, so we have to increase it. This current is reducing, so the magnetic field which is toward this side, that is reducing, we have to increase it. So how to increase it? You have to support in the same direction. So if you want to support in the same direction, the current should be this way. So the current should be this way. That's how you have to find out. Now you see here, if this arrow mark was upside, that is, if the current was increasing, what will happen? It should be opposite. Okay, now here you see in this one. Here, the same thing. This I am not told whether the current is increasing or decreasing. Okay, we'll take the current. This current I is increasing. If the current is increasing, you see here in this loop A, it is going toward that side. So the magnetic field is this way. Here it is into the plane of the paper. So this magnetic field is increasing. We have to reduce it. So it is already toward this side. We have to reduce it, means you have to make it toward that side. So it should be like this. So it should be like this. And here if you do, you will get opposite because the magnetic field direction is different. So this is how you have to use Lenz's law. So Lenz's law, you see here, first this type, you should practice how to do this one, whether north comes or south comes. This is not just for this single loop. In the case of solenoid also, it can come. The solenoid is like this. And if you push something from here, then also the same situation you have to use. So this type you should do. After that, you should do this one. That is this. In this one, when you are taking out, how it works. When you are taking from outside to inside, how it works. When it's moving inside, no EMF. Inside, when it is increasing the area, what to do, that also you should know. And afterwards, when you are taking different shape from here to outside, if the shape is different, what will happen, that also. So so many types of questions are there, but one type of question is having a very high chance. Any one of this one can come for examination, because this is the most important part in that one. Okay. So that's over. Now we will go for motional electromotive force, motional EMF. So here, this is the next topic, okay, because we spent too much time on that Lenz law. This is the next topic. This is also important. So this motional EMF. So here, this diagram is to derive the equation for motional EMF, how much will be the EMF. So you don't have, think about in such a situation. If you have such a setup, then only the EMF will be induced. It's not like that. When you have a conducting wire or a rod which is moving in a magnetic field, there will be an induced EMF. That is, you have a wire like this, a conductor like this. This is moving in a magnetic field. So one side will become positive, another side will become negative. There will be a EMF. So to show that how much that EMF, we are doing this. So you should not have a confusion or a idea that if you have a loop like this and this is moving over this one, then only there will be a EMF. It's not like that. If you have a single wire which is moving, then also there will be a EMF. For example, if you drop some rods from a particular height in Earth's magnetic field, then already Earth is having a magnetic field. Actually, now it is out of syllabus, the direction and the horizontal component and all. That's why no need of going detail into that one. But you should know that there is a magnetic field for the Earth. And the direction of magnetic field, Earth's magnetic field is from south to north. Not from north to south, it's from south to north. Okay. So I'm not going to the details of that one because that part is not there, I think. So when you drop a wire or a rod in the from the sky, due to the magnetic field, Earth's magnetic field, there will be an induced EMF. Or even for an aeroplane, when an aeroplane is flying in the Earth's magnetic field, the two ends of the wings, there will be a induced EMF. So how much it is? So that can be obtained using this one. So even for the aeroplane, problems used to come for the examination. Now, I don't think it will come because the Earth's component we are not discussing now, Earth's horizontal component. Okay, we'll see that one, whatever. Now, here we are going to derive it. So once we will go for the exact situation. So see here, this is our rod. Okay. So what we are doing is, we'll take from this much of only the effective length. Okay. This length of this rod is L. Total length, actually we are discussing only about this much length. Okay. This much length only we are discussing. It can be the total length also. Just now we are discussing this much length as L. Rod of length L, which is moving in the magnetic field perpendicular to it. So the magnetic field is into the plane of the paper and it is moving perpendicular to it in this direction with a velocity V. So we have a velocity v and it's moving in this direction. I think it's clear. So when it is moving like this, some induced EMF will be there. So we have to find out how much is the induced EMF. Its derivation we will do. Actually, this derivation you might have done, just as a revision we will do. So what is our equation for EMF, induced EMF? Is equal to minus d phi b by dt, because we will deal from what we already studied. Okay, so this flux is required here. Minus d phi by dt means we need the flux here, phi b. So how much will be the phi b here? That will be b dot a. So here you see here it is perpendicular, so dot will not have any meaning, just b into a. Okay, so what is b here? B is mentioned as b itself, so I will write it as b itself. And area means we are thinking about this loop. So this much area we have to take. Okay, so this much area when you are taking, this is at a distance x and this is L. So it will be B into L into X. So this is the magnetic flux. So we have to use this equation d phi by dt, and in that one phi we got this much. Now what is EMF? That will be d by dt of this one, B L X. D by dt of B L X. Now you see here when you take derivative, this constants you can take outside. Here the magnetic field is same everywhere. So B we can take outside, and this L also not changing, so that L also we can take outside. Then we have to take the derivative of d by dt of x only. This minus sign is there only. So what is dx by dt? So it is moving, the x is the distance. So dx by dt, what is dx by dt? Dx by dt will be rate of change of position, that is velocity. But one thing you see here, this x is reducing. So here this dx by dt is equal to minus v, because x reduces. That's why it's minus v. So this one we can substitute here. So our induced EMF will be B and L is same only, and a minus sign is there, and V is minus V, so it will become plus. So the induced EMF is given by E is equal to BLV. Okay, so this is the final equation. So now you see here, now after getting this derivation BLV, you forget about all these things. That is, this square is not an important thing here. If you have only one rod in the magnetic field, then the induced EMF is BLV. That is, B is the magnetic field, L is the length, and V is the velocity. So it depends on the velocity. Okay, so this is when it is moving perpendicular to the magnetic field. Okay, when it is moving perpendicular to it, we have BLV. So this is the induced EMF when a metal rod is moving in the magnetic field. So based on this one, questions can come. So you should be very much careful about this one. And one more thing you should know, this is moving perpendicular to this one. If it is moving parallel and all, it won't work. Okay. And one more thing, this electromotive force, EMF, you studied in the previous chapter. So you should have the concept of that only. Electromotive force, it is not a force actually. Okay, just the name came like that. That's all. So EMF means the potential, you take it as the open-ended potential difference. That's all. It's nothing related with force here. Okay, so we have EMF as BLV here. The same you can get in another way also. That is the same BLV equation we can get in another way. This is that what the same concept we are deriving based on another situation. That is, you have the same loop like this. Our L is moving like this with a velocity v here. Now we are discussing about the work done here. Based on the work done, how we can explain this one. See here, some electrons will be there in this one. So these electrons will be moving here. So how much will be the work done? Work done is force into displacement. So work done will be, work done is equal to force into displacement will be there. So force into, here this displacement is moving at length. L. So this work done will be, how much is the force? When a charged particle is there in the magnetic field, the force is given by QVB, which we already studied in the previous chapter, into L. So this will be the work done. That is, the electrons are moving in this one. Okay. So when a charged when a metal rod is moving like this, the electrons will experience a force and it will move like that. So the force is given by QVB and it is moving a distance L here. That's why the work done will be that one. I think it's clear. That is, once more, those who not understood, we have a magnetic field which is into the plane of the paper. You don't even think about this one. You just directly take that you have a magnetic field like this and you have a rod like this. When the rod is moving, the electrons are moving like this for the whatever with the charge. Okay, here electrons only. So where electrons are moving, there is some work done. So how much is the work done? If you want to calculate, work done will be force into the distance. So force is the force acting on the charge. So when a charge is kept in the magnetic field, the force is this one, QVB. V is the velocity. So the into L will give the work done. Now we have the E, or the E means EMF, or you know that E and V are same only for the open circuit. So that is given by what is potential difference? Work done by charge. So it is work done by charge. Already we have work done here. This one. So what we can write? This E is equal to work done is QVB into L divided by charge Q. So this Q cancels. This is B is here and L is here and V again. So this EMF will be BLV. So what is the difference between this one and the next one? Both are same only. This one, we are using a particular concept of this magnetic field and we are getting the this one EMF, induced EMF as BLV. Here we are thinking about the mechanical work done on the electron and we are calculating, then also we are getting the same equation. So the induced EMF will be BLV. So that's about the motional EMF. So motional EMF also you can get a numerical problem directly. You can get a numerical problem on that one. How much is the induced EMF in that one? Okay. So I think this is also clear. All these things you already done in the class once, and this one is as a revision, just revising once before going to the pre-board examination or before doing more problems on that. Now we will move to the next one, inductance. So inductance, before going to this inductance, I think you are aware of the capacitance. So we have a capacitor. First, before inductance, we'll just discuss about that. We have a capacitor like this. This is a symbol for capacitor. We have a parallel plate here. So when we connect this one to a battery or a cell, what happens? This one will store charge. This side will be positive, plus Q, minus Q. It will store charge there. So this device is called as capacitor. And it will store charge. It can store energy. So that how much it is storing, that depends on the capacitance of the capacitor. I think that's clear. That is, we have a capacitor here, and this capacitor stores charge, stores energy. So that depends on the capacitance of the capacitor. Now, same way we have inductor here. In the capacitor, in which form the energy was stored? I think you remember that one. In capacitor, energy is stored, that you know, energy is stored in a capacitor, equation half CV square and all you done. So in which form this energy is stored? In capacitor, the energy is stored as potential energy. Which potential energy? Different potential energy is there. In capacitor, the energy is stored as electrostatic potential energy. Very important. In capacitor, the energy is stored as electrostatic potential energy. Now, here we have inductance. Inductance means, inductor means it is a coil actually. Just like a solenoid. This is called as inductor. Just like capacitor, we have a coil, means that's called as inductor. For this inductor, we have a value. Just like capacitor, we have capacitance. For inductor, we have inductance. So the inductance is not this one. This is called as inductor. And for this inductor, we have a inductance that says how much energy it can store. So that we will discuss later. But you should know that what is when you are using the word inductance and inductor, this inductor is having a inductance. Okay. Now, see here, if you have a coil like this, if you keep this coil in a magnetic field or in a changing magnetic field, what will happen in this one? Some current will be induced. And you studied it happens in the opposite way also. That is, if you keep this coil in a magnetic field, in this one a EMF or a current is induced, or if already you have a current inside this one, it can induce a magnetic field also. So it works in both ways. So in the case of inductor, if you already have a current in the inductor, it produces a magnetic field. Or if you are keeping this coil in a magnetic field, it will induce a current in that one. In both way it works. So there is a relation between the flux and the current. So if a current is passing through that one, it will produce a flux, or if it is kept in a changing flux, a current is induced. So the relation is given by, already we discussed, it is when there is a change, then only it will work. So we have d phi b by dt. This is proportional to di by dt. That is the flux. The rate of change of flux is proportional to the rate of change of current. Okay. Or we can write this n phi b is proportional to I. Okay. So when you n, why we are taking, because we have more number of turns means. So here, when you remove this one, there it comes a proportionality sign. That is, that constant of proportionality, that is called as the inductance. I think that's clear. That is, we have d phi b by dt is proportional to di by dt. That is, the rate of change of flux is proportional to rate of change of current. The constant of proportionality, that is called as inductance. So actually, why I'm not writing inductance here means, actually you can write it L like this. But we have self-inductance and mutual inductance separate. So sometimes you'll write L and sometimes you'll write M. Okay. So generally for inductance, we will use L. L is for inductance. I think that's clear. So with the constant of proportionality in this one, that is called as inductance. Now, the inductance, we have a unit for inductance. Okay, we have a unit for inductance, that is Henry. Okay, that we'll discuss later. So you should know the inductance. So we will write it as L, and sometimes M also is there when it comes to mutual inductance. So the unit of inductance is Henry. Now we will discuss the self-inductance and mutual inductance in detail. Separately, what is self-inductance, what is mutual inductance, we will discuss. Okay, so we'll study about mutual inductance now. Okay, so first you should know what is mutual induction. In 10th standard, it was there previously. What is mutual induction? That is, if you have one coil and in the vicinity of that coil, we have another coil. So in 10th standard, how you done the mutual induction means, you had a non-conducting rod like this, and we had a coil here and another coil here, and in this one we had a battery and a key, and here we had a galvanometer. This was there in the 10th standard level. And what we can observe is same as the first experiment what we done here. This rod is there, that's all. Okay, the first experiment we done, when you tap this one, it will induce a EMF in this one, or it will show a deflection, that's all. So that is called as mutual induction. That is, a changing current in one coil can induce a current in the, or EMF in the nearby coil. That is called as mutual induction. Okay, not working. Okay, so a changing current in one coil can induce a current in the nearby coil. That is called as mutual induction. Now, here you see here in this picture, we have two coils. So we have an outer coil and an inner coil. So when you, this is same as a textbook picture, okay. So you see here, this outer coil, all suffix we taken 2. And for inner coil, we taken 1. So the inner coil is having a radius of R1 and the outer coil is having a radius of R2. And the number of turns in the inner coil is N1 and outer coil it is N2, like that we take. Okay. Now we have the coil, one coil inside and one coil outside. Okay. So actually this one can be kept outside or different orientation. So it depends on the orientation also, that we will discuss at the end. Here, to get the maximum efficiency, we will keep one coil inside the other coil. Now, to study the mutual inductance, what we will do is, both are having length L also. So here what we are doing is, we will do in such a way that we are passing a current in the outer coil, that is I2. We have a current in the outer coil, this one, we are sending a current I2. So when you send a current I2 in the outer coil, what will happen? That will produce a magnetic flux. And the inner coil, that is S1, is kept inside this big coil. So in that one, it will induce a flux. I think that's clear for you. That is, once more, we have an outer coil and we are sending a current I2 through that one, and that produces a flux, and the inner coil is kept inside that flux. So the flux linked with the inner coil, listen carefully, the flux linked with the inner coil due to the current in the outer coil. That's given by this equation, that is N1 phi1. See here, this suffix you have to see. This is the flux linked with the inner coil. That is proportional to the current passing through the outer coil. That is I2. Now, here we have to replace this proportionality sign with a constant. So N1 phi1 is equal to M12 into I2. That's what written here. Okay. So M12 into I2. What is this M12? I told you for inductance we will use L or M. So this M is called as the mutual inductance. It just says that how much coupling is happening here. So M is called as mutual inductance. Then why this 1 and 2 is coming here? Because this is mutual inductance of 1 with respect to 2. Mutual inductance of 1 with respect to 2. Okay, later we will see that a mutual inductance of 1 with respect to 2 and 2 with respect to 1 is same only. Okay, so this mutual inductance of 1 with respect to 2, we can write like this. Now, our next task is to find out the value of this M12. So that is very easy because we have these two sides. So we will see what is this side. This N1 phi1 is equal to, what is N1 here? This N1 means number of turns in this one. That is from here to here in the first coil, that is, this is smaller coil, how many number of turns are there? That is N1. So how much it will be? That is N1 into L. What is this small N1? This is the number of turns per unit length into length. That gives the N1. I think this is clear. This part is N1 is number of turns in the inner coil, that is equal to N1 into L. Now we have phi here. What is phi? Phi is equal to, what was that? Area into magnetic field, or B into A, B dot A. Okay. So how the area you will get? Area of this smaller loop, it is having a radius R1. So the area will be pi R1 square. So I think you got it. This N1 is this one. Flux is this part is area. Okay, this is area into magnetic field B. So what is the magnetic field? Now magnetic field inside a solenoid, that is mu naught Ni. When you take this mu naught Ni, very important, this magnetic field is produced by the outer coil, not the inner coil. So when the magnetic field is produced by the outer coil means For the outer coil, the number of turns should be N2 and the current should be I2. So totally what you will get, this one N1 phi1 is equal to this one mu naught. I will take this all things in a arranged way. I will write N1 N2 pi R1 square L into I2. Okay, now what is our equation here? This is equal to M12 into I2. So you see here M12 into I2 is equal to this one mu naught N1 N2 pi R1 square L into I2. So this one will be this much. Remaining I2 same. So M12 is equal to mu naught N1 N2 pi R1 into L. So the mutual inductance is this one. So see here, what are the things depends on mutual inductance? Mu naught. Mu naught is about the permeability. Okay, permeability of free space here, because we are discussing in a situation where this inside this one is empty. And N1 is the number of turns in the smaller coil, N2 is the number of turns in the bigger coil, and pi is there. Then R1 is the radius of this one, and L is the length of that one. It depends on all these things. Okay, so this is the mutual inductance of which one? Small coil with respect to the big coil. But this is not the end. We have to do it in the opposite way also. If you send the current to the smaller coil, it will induce a current and a flux in the bigger one also. So how much it will be, that we will discuss now. Okay. So this is for that one. Okay, picture is not there, but you should know the same situation. So here you can see here I1 is there. So current is passing through the inner coil. And so we'll write the flux in the bigger coil is N2 phi2 is equal to M21. Previously it was M12. Now it is M21 into I1. So same thing you will go N2 phi2. N2 means number of turns in the big coil. So that will be N2. That is, this is number of turns per unit length into length. This is N2 into pi R1 square. Okay, I will write pi R square. Whether 1 or 2 will decide later. Then afterwards magnetic field. So magnetic field is produced by the smaller one, which is mu naught N1 I1. Okay. So this is the magnetic field B. This is N, no doubt in that one. This is area. Okay, just like the previous equation. But only difference or only problem is about this R. Because in the previous one, see here, it was R1. That is, this is R1. We are taking the area of the smaller one. Bigger one is producing the magnetic field and we were taking the area of the smaller one. And if you take that logic, in the next one, here it should be R2. Because the smaller one is producing a magnetic field and the bigger one. So we have to take about the bigger one. But here you can see in this equation, here they are written R1 only. So this is R1. So why it happens like that? That is an important. Here, this is the only confusing thing in that. See here, you have one coil like this, big one. We are facing from this side, and you have a smaller one inside. First case, how it was, this one produces a magnetic field, and the smaller one receives it. So the area which receives was this much only. The flux which is receiving is this much only. That is, the bigger one produces, and the smaller one takes it. Okay. So if you take this one, big one produces and the smaller one takes it. So how much will be the area where which is taking is this one only. That's why this R1 was kept. And now in the opposite way, now what we can do, when this one produces and this one receives, that time also you have to take the smaller area only. Okay. So in this case, you see here, that's why this R1 comes here. Okay. When this one produces and this one receives, then also it will be in the R1 only. So that's why we got R1 here also. So here you see, when you substitute that one, you will get M21 is equal to the same. Now you see here, this M12 is equal to M21. So we can simply call it as M. So the important thing in this one is, if you have two coil, the mutual inductance of first coil with respect to second coil, or second coil with respect to first coil, both are same only. Clear? So the mutual inductance of first coil with respect to second coil, or second coil with respect to first coil, both will be same. Now, here you see, this case was in such a way that you have one coil here and you have another coil here, and inside it was empty. If inside it is not empty, what will happen? If inside it is filled with some material, then we have this equation. You see here, previously we had mu naught. Here we have mu r, which is the relative permeability. So you have to replace this mu with mu r into mu naught. That is, the m will become mu r into mu naught, and the remaining thing is same. This one can be replaced as mu also. Sometimes we can write m is equal to mu into n1 n2 pi into r1 square into. What is this mu? Mu is mu r into mu naught. Okay, so that's about our mutual inductance. So same way we have self inductance also. So now we will discuss about self inductance. So the self inductance is when the self inductance comes, you see here, this is about the single coil. Okay, so we have to move a little bit fast now. Okay, so we have a single coil here like this. We have a single coil, and what happens is, when a current is passing through this coil, a EMF is induced in the same coil. The EMF is induced in the same coil, so that is called as self-induction. I think the concept is clear. That is, when we have a coil and the current is passing through this coil, and it induces a EMF in the same coil, that is called as self-induction. Okay, so this induced EMF in this one, that's also called as back EMF. Okay, we'll move a little bit fast. That is, the EMF induced in this one is back EMF. Okay, so we'll go for the derivation of that one. So see here current is passing through this one. So we have now N1, N2 is not required because only one is there. Okay, it is proportional to I, and here you can see N1 into phi B. The proportionality constant is L into I. Okay, now just the same way we can take what is N phi B? N phi B is equal to, N is the number of turns, so it will be N into L, and this flux will be area into magnetic field. So mu naught into N into I into area. So we are taking it as area itself, because previously taken R1, R2 and all, because we had two. So we will get this one as mu naught N square A into L into I. So what will be L now? L is equal to N phi B by I. How we are getting? Because this equation also is there, na? That is EMF is equal to d phi by dt. So EMF will be minus L into di by dt. So you will get from there. Okay. So you'll get L is equal to d phi b by dt. You will get. So L is equal to mu naught N square A into L. Okay. So this is the equation for self-induction, same as the mutual inductions there only. Only difference is in that case we taken this pi r1 square. Here instead of that one, you are directly writing it as A itself because only one coil is there. And when you fill this one with another one, when you fill this with one more coil, then what will happen? When you fill this inside this one with any other material, inside this one some material is there instead of mu naught, then it will become mu r. So L will become L is equal to mu r into mu naught into n square Al. So this mu r into mu naught, that can be written as mu also. So L is equal to mu into same n square A into L. Okay. So this mu is called as the permeability. Okay, that is the permeability of the medium. Mu r means it is the relative permeability. Here it is just permeability. So that's about self-inductance. So self-inductance, when it is coming, you have to write L, and otherwise mutual inductance means it will be M. Okay. Now, if you have both coils, what to do? If you have two coils, okay, that we will discuss after this energy stored. Okay. So here we are discussing about the energy stored. So work done is stored as magnetic potential energy. That is, we are charging this inductor. So in the inductor, the energy is stored as magnetic potential energy. I think you got the difference. This is important. Okay. When we had the capacitor, the energy stored in the capacitor, as electrostatic potential energy. Here it is stored as magnetic potential energy. So that is different. So here magnetic potential energy, because many times this question came, 1 mark question and all, it will come. So you should know that it is stored as magnetic potential energy. So how much will be the energy stored in this one, that we have to discuss. So you see here, the power. What is power? Power is rate of doing work. That is dW by dt. That is called as rate of doing work is called power. In mechanics or everywhere, it is same only. And in electricity, the power is given by V into I, or it is same as E into I. Okay. E is the EMF, V is the potential. Both means the same only. Now, see here, for EMF is given by L di by dt. Okay, plus or minus you leave it, just L di by dt you will get. So now what we can write, the power is given by dW is equal, dW by dt is equal to, already one I is there, and for this EMF we have L di by dt. So it will be equal to L into I into di by dt. This L and I are constant, we are taking it outside, and okay, like this, L into di by dt you can take. Now, to get the total work done, you have to integrate this one. So when you integrate this one, you will get work done is equal to integral dW is equal to integral 0 to I Li di. The more mathematical part we are not going, just on doing this one, you will get work done is equal to half Li square. Okay. So this is the work done. So this work done will be stored as its potential energy. So the work done in the inductor, when you are charging the inductor, the work done is given by half Li square. So this half Li square is stored as magnetic potential energy. You can think this one as similar to half CV square. So okay, there it is half CV square, here it is half Li square. Okay, so you see here half makes same half there. For capacitor it is C, and inductor it is L. There it is voltage, here it is current. Okay, so you can remember like that. So in capacitor it is half CV square, here it is half Li square. I think this is also clear. We have half CV square and half Li square in the case of our inductor. Now you see here, in the actual situation, when you have two coils, you have one coil and inside that one, another coil will be there. So when the current is passing through one coil, what will happen? It will have two effects. Or you think about the current is passing through both coil. You have two coil and current is passing through both coil. For that coil, two effects will be there. One is the effect due to the current in the same coil. That is called as self-induction. And in the other one, it is mutual induction. So what you have to do is you have to add both equations. This EMF of the same coil due to self-induction and mutual induction, both equation you have to add. That's all. Okay, so the total EMF you will get like that. Okay, both will happen at the same time. Now here one more point I want to tell. Okay, we'll move to the next topic. That is AC generator. So we have to study about AC generator. Actually, I thought of one more point. I am not getting into what I thought of telling. Work done in the potential energy of L square. Okay, we'll think of that one later. So we'll now go for this AC generator. Because our next topic is AC. That chapter is AC. So before that one, you should know how this AC generator works. Okay. So here you see, we have a coil which is kept in the magnetic field. We have north here, south here, and a coil is kept in the magnetic field. And in this magnetic field, when this coil rotates here, and the coil is rotating here, we will have a flux here, and because of the change in flux, a EMF will be induced. That's the working of that one. We have a coil here, and that coil's area and all we'll discuss. And when it is rotating here, there is a change in flux, and we have a rate of change of flux. Due to that one, a EMF will be induced here. And these things, you know, the slip rings. That is, we have two separate rings here for AC. For AC generator, we will have two separate rings here. So this is just there will be a connection till it's sliding over that one. Okay, and this is opposite. What is that? In the case of DC, we will have a same single ring. It is splitting into two. That's called a split ring. We have like this for DC, and in the case of AC, you have one ring like this and another ring like this. It is separate in the case of AC, and in the case of DC, you have single ring splitting like this. For just for motor and generator, it is both like that only. Okay. Now we'll go for the actual calculation of this one. So this 5B magnetic flux, 5B is equal to, here the general equation BA cos theta. Now theta is the angle turned by this one. When it is rotating, the angle turned this one. So we can write it as BA cos omega t. What is this omega here? Omega is the angular frequency of the rotation of this one. This coil is rotating. Its angular frequency is omega. So t, when you multiply with omega into t, you will get how much angle it turned. Now the EMF is given by, EMF is equal to minus n into d phi b by dt, which is equal to minus n into b into a d by dt of cos omega t. So you'll get EMF as n b a. When you are taking this derivative of cos omega t, you will get minus omega into sin omega t. So you can write EMF as E0 sin omega t, where this E0 is this much part. Okay, so E is equal to E0 sin omega t. So this omega you can write in terms of frequency also. So the E will be equal to E0 sine 2 pi nu t, where this nu is the frequency. So the frequency of this AC will be same as the frequency of the rotation here. When this generator is rotating, that rotation frequency and this frequency will be same. I think that's clear. When it's rotating, the frequency of that one and the frequency of this will be same. Okay, now this just this part, when we are doing it as a wave, how it will be, that we will discuss. So only point which you should remember is the EMF is given by this one. E is equal to NBA omega sine omega t, where this one you are writing as E0 or the maximum potential of that one. Okay, so now we will see the graph of that one. So this is the last one in the chapter. Okay, so I see here, here what happens is, first the coil is like this. When the coil is like this, coil is having a direction like this, because when the coil stands like this, the direction is like this. So here you can see our equation. If you take E0 sine omega t is there. Okay, so when the angle is 0 here, the sine value will become 0 here. So the EMF starts from here, and what happens when it turns like this, it becomes maximum here, that is after 90 degree. Okay, after pi by 2 it becomes maximum, so the EMF goes to the maximum value here. Now what happens is, this turns to the opposite direction like this. So previously it was like this first, here it turned like this. Here, from here again one more turn, so it comes this side. So if you notice here, you can see this RS became down here. So one full half round comes, means it is reaching here. Then again, in this case, here you see the area was down, here area is like this, here the area goes up. So it becomes negative maximum here. Then again from here, it is coming here. So it will become a full cycle. Clear? So in a full cycle, it makes one wave. So if you take time period from here to here, it is the time period is t here. This is t by 2. Like that you will get. Okay, so now the thing is, in this graph, we written that E0, that E0 is this voltage. This voltage is E0. Okay, so when we come to the next topic, we will discuss that one in later. This is called as the peak voltage. So this how much it is going up, this is called as peak voltage, and this one down, this is minus peak. Okay, this is peak and this is also minus it. So this voltage is called as the peak voltage. From here to here, this total, this is called as the peak to peak voltage. So when AC generator is moving, you will get a wave like this. Okay, so same in the case of DC generator, the difference between this AC generator and DC generator is, in DC you will have like this. Okay, actually the original DC which you are getting from a cell is a straight line like this. In the case of a DC generator, you will get like this. Okay, not a straight line like this. DC generator will be like this, and AC generator will have positive and negative sides. Okay, so one terminal will be, if you take it as 0 potential, the other will go from 0 to positive for the half cycle, and the remaining cycle it will go to the opposite direction. That's how it works. I think this is clear. So the theory part of the full chapter almost we discussed. The entire thing we discussed, I think. And based on this one, we had to do numericals, or actually more than numerical, 1 mark questions will come from this chapter actually. Okay, this chapter, more 1 mark questions will come. And after this one, actually AC and EMI is almost a continuation. So we will discuss along with this one little bit about AC also, and later we will go for its numerical part and all. Okay, so Okay, so we'll discuss something about AC, because just now we discussed about our AC generator. So from AC generator, we are getting a wave like this. That's called as AC. Now we'll discuss more about this AC, and when we apply AC to this one. Okay, so when we apply this AC, okay, so when we apply AC to resistor, what happens when we apply resistor to when we apply AC to our capacitor, what happens? All those things one by one we'll discuss. Before that one, first we will see what is this AC means. Okay, so this our topic is this AC applied to a resistor. So along with this one, we'll discuss, that is when we are applying AC to resistor. Along with that one, we will discuss how we can understand what is this AC, how the AC current works. Okay, so here you see here, the first point is here, this is the source of AC. Okay, so generally in DC, the source of DC, a battery or a cell, we used to draw like this. Now in the case of AC, we will draw this one. This is the source of AC. That's the first thing you should know. Okay, so we have a resistor which is connected to this one. Okay, now AC, first if you consider AC as a wave, we can write this AC produced by this one as V. So V means it is varying with time. You know, AC means it is varying with time. So this V is given by V is equal to Vm sine omega t, like that you will write. What is this? V is equal to Vm sine omega t. Our AC wave is like this. It is like this. Okay, so this maximum, this one is called as Vm. It changes like this. So you see here, at a particular time, for example, if you have a time here, this axis can be time. Here at this point, what is the value of AC? This one, this is called as V. So how we can get the value of V? V is equal to Vm, this maximum value, into sine of this omega t, this one. Okay, so that's how you will get. So this, I think the concept is clear. This Vm means this maximum height. This V means you can divide the time here, a particular time. At that time, what is the value of V? That is called as V. So V is the instantaneous voltage. This Vm is the height of this one, the maximum value or the amplitude of that oscillation. Okay, so V is the instantaneous voltage and Vm is the amplitude of, so the wave goes like this. Okay, so if you know this one only, the remaining will be easy. Now V is equal to Vm sin omega t, we return. So V is equal to Vm sin omega t. And what about if it is cos omega t? Nothing wrong in that one. Actually, the sin omega t, the starting point will be different. That's all. Okay. So V is equal to Vm sin omega t is the source here. Now see here. So such a voltage is applied to a resistor here, resistor R. We have a resistor R here. So this is connected here like this. Now we have the Kirchhoff rules. So here you think it is just like DC. Here we have a battery and here we have a resistor. So how much is produced here, that will be dropped across this one. So using Kirchhoff rule, what we can write? Vm sin omega t minus IR is equal to 0, or is equal to I into R. You see here I am writing this small letter I. So in AC we will use small letter. In DC we will use capital letter. Okay. In AC also, when RMS comes, we will do it. That we will discuss later. So this I small, whenever we are writing small letter, it just means that it is varying with time. So Vm sin omega t is equal to IR. We written like this. So from this one, we can write I is equal to Vm by R into sin omega t. So this Vm by R means maximum voltage by resistance. That will be the maximum current. So we can write I is equal to Im sin omega t, where this Im is equal to Vm by R. That's the maximum current. Okay, so That's the first part. That is, we have a resistor here. Once more, in the resistor, we have a source here, which is producing V is equal to Vm sin omega t. This Vm means maximum voltage. This V means the instantaneous voltage. And omega is the frequency, angular frequency of that rotation or the wave. Now, see here, when you apply that one, we can apply the Kirchhoff rule here. So Vm sin omega t is equal to IR, you will get. On rearranging, you will get I is equal to Vm by R into sin omega t, you will get. This Vm by R means maximum voltage by resistance will be the maximum current. Now, you can see here, what is voltage? You see Vm, a maximum value into sin omega t, and current is Im into sin omega t. So if you draw a graph, see, you can see that this blue color what you are seeing here is, this is voltage graph and this is current graph. See here, it doesn't mean that always the voltage graph is bigger and the current is, because this is two different scales. This voltage scale and current scale depends on the what scale you taken and what the value of resistance. This current, if it is bigger than voltage, also nothing wrong in that one. Okay, so generally we are dividing with something, that's why you taken lower, that's all. If it goes up also, nothing wrong in that. So this is the voltage and this is the current equation. But our main point is not about this height, about this side. You see here, when in both equation, when this is omega t is 0, both are at 0. When this omega t is 90 degree or pi by 2, both are at maximum. And when this is at 180, both are at 0. So we can say when it goes maximum, when it goes to 0, when it goes to the negative maximum or minimum, that is same. So the meaning is the voltage and current are in phase. That is, there is no phase difference between that one. So that's the first point. When current is passing through a resistor, that is when AC is applied to a resistor, we have a voltage, we have a current, but the voltage and current are in phase. The technical term is in phase. In phase means like this. The graph, both are, one goes like this and the other goes like this. Okay, both will be maximum at the same time. Both will be 0 at one time. Both will be negative maximum also at the same time. So the voltage and current are in phase. That's the main thing. Okay, so that is in the case of AC voltage applied to the resistor. I think that concept is clear. In resistor, voltage and current are in phase. Okay, there is no phase difference like this. Okay, now we are thinking about the power dissipated in the resistor. In the resistor, there is some power dissipation. Okay, so the power dissipated, how to get power? Power P is given by I square R. Okay, so what is I here? P is equal to I is equal to Im sin omega t. You have to take square of that one into R. So power will be equal to Im square R sin square omega t. So this is the instantaneous power. Okay, at that instant, what is the power? But we need the average power, because instantaneous power means for a very short time. We need the average power. So you see here, when you take the average power, you'll take average of this one. When you take average of this, you see here, we have Im, which is a constant value, so Im square and R. And what is coming to take average is sin square omega t. Okay, this symbol is for average. Okay, so this Im square into R, it's a constant we are taking out. Then average of sin square omega t. So what is the average of sin square omega t? You know the sin theta value, it starts from 0, goes to +1, comes back, same. This one, from 0 starts, go to maximum, come to 0, and goes to the minus side and comes here. So if for sin theta, if you take the average value, it will be 0. But when sin square comes, this negative side, when you square, that also will become positive. So the value becomes from 0 to 1. The average of 0 to 1, that one will be half. So this part will become half. So the average power is given by Im square into R by 2. Okay, so this is important now. It is Im square by 2 into R. Or we can do in another way also. This power is equal to Im divided by root 2 square into R. So we are getting power like this. Power is equal to Im by root 2 square into R. So why we taken this Im by root 2? That's important now. Why we taken this Im by root 2 here? The power is Im by root 2 square into R. If you take the case of DC, what is power? Power is equal to I square R. The power is given by I square R. In AC, it is Im by root 2 square. Now you see here actually the current, if you take this as current I, this current goes to maximum here and it is coming. So when you take the average power, whether we have to take current as this one and this one, or if you take the average current, what happens? This positive side and negative side will become, that average, that will become 0. For the full cycle, it will become 0. But you know this AC also is doing work, the average is not 0. So in this case, if you compare this AC and DC, the effective value of AC when you are comparing with the DC is Im by root 2. So this is called as the RMS value. Okay. So this IRMS is equal to Im by root 2. So what is this IRMS means? That is AC current is increasing and decreasing, it is varying. So when it is varying, the equivalent value of that DC, that AC to DC, that is called as IRMS. So see here in this graph, you can see it starts from here and it is going up like this up to Im. And this is the RMS value. So I will draw a little bit bigger. So it goes like this. So this is our Im. And this is the RMS value. That is Im by root 2 or 0.706 Im. This is the RMS value. So this RMS value is the effective value of AC. That is, it is equivalent to a DC of that voltage. So that current. Voltage also same thing only, that we will discuss later. So voltage and current, if you take the RMS value, means maximum value divided by, that is we have voltage Vm. So this RMS value of voltage is Vm divided by root 2. Okay, so we will do some problems on that one. Then you will get a clear idea about that one, what is this RMS value is about. And the basic thing is, when you compare AC and DC, the AC will vary from 0 to maximum value and it will come to a negative side also. So the effective value of AC is that maximum value divided by root 2. That is called as RMS value. But one thing is there, when you get a problem, AC voltage of 100 volt or AC current of 3 ampere. So this AC is the RMS value. If you have a voltmeter and it measures and gives you 100 volt, this you will have a confusion whether the 100 volt is AC volt, the maximum value, or RMS value. No need of confusion. If it is not mentioned, if the value is just given, means that is the RMS value only. If it is mentioned it as the maximum value or the peak value, then only you have to take it as RMS value. Sorry, you have to take it as peak value. Otherwise, it is RMS value. So if a question comes, AC current of this 5 ampere and DC of 5 ampere, which produces more power, then both produces same only, because both AC and DC, it is the situation is same. But if it is given as peak value, then you have to take that. If the peak value is 5 ampere, then the actual value or the effective value is 5 ampere divided by root 2. That's what you have to take. Okay, so that's about now. Our time is almost over. So I will stop now. So we will see later at 2:30. Okay.
Small clicks.